I have gotten a few emails from students asking questions about the homework. In particular, something that I had mentioned in one of the previous videos, given a set of something, vectors, polynomials, matrices, determining if that set forms a vector space or not. And in the videos I made before, I went through how to determine if something is a vector space or not, and we worked through one or two. And then in one of our follow-up videos, we kind of realized that there's actually a shortcut way to determine if something is a vector space. Essentially by looking for closure under addition and multiplication, scalar multiplication. But ultimately, you need to be able to determine if something is a vector space using all 10 axioms or by the shortcut method. So for the purposes of this video, I'm just going to go through one or two of them to determine if something is a vector space or not, using all 10 axioms. I may not actually write all of them out because once you do one or two, the idea is pretty straightforward. And just as a guideline, all things being equal, things like associativity, distribution, all that will generally hold for most of the operations and most of the things we work with, unless you kind of go out of your way to make it somewhat bizarre. It is generally things like closure, either under addition or scalar multiplication, that tend to cause problems, which is again also, if we recall the shortcut, the thing we actually really look for to determine if something is a vector space. Because basically, if the closure things hold, then there's a good bet you're going to have a vector space. But again, I just wanted to work through a few of these, and the questions I got in particular were that the ones I had looked at in the video were essentially polynomials. But yes, you can create a vector space of anything as long as it's defined. So in your homework, you have matrices, you have polynomials, you have vectors, and how you go back and forth between them. And the good thing is, you actually don't, but we'll see that as we go through here. So I'm going to kind of go back and forth in my book because, again, we want to write this out formally, so we're going to do it formally like the book. This is section 4.2, page 166, and then we're going to be using the axioms at the beginning of 4.2 here to determine if something is a vector space. So, testing for a vector space. In exercises 13 through 36, determine whether the set together with the standard operations is a vector space. If it is not, identify at least one of the 10 vector space axioms that fails. So first off, number 13, M46, which means the set of all 4 by 6 matrices. I want to determine if that is a vector space. So now I grab multiple bookmarks again. So we can do this formally by the book. Check the 10 different axioms. Addition, U plus V is in V. What that means is I pick 2 elements of this set. So I will say M1, 4 rows by 6 columns. So we'll just say M11 to M16, M41 to M46. There's my first element. Pick another element. We'll go with, I need a different letters because I'm going to have to keep using that notation. We'll go with N1, which is N11 out to N16, N41 out to N46. So now I have 2 4 by 6 matrices. I need to know if it's closed under addition. So what is M1 plus N1? That's equal to M11 plus N11 over to M16 plus N16, M41 plus MN, I can't keep saying M and N, N41 over to M46 plus N46. Because all we do is add component-wise. But these are all real numbers when you add them, which means this is just a 4 by 6 matrix, so it's closed under addition. Number 2, u plus v is v plus u. I already have two m and n right there. I need to show that m1 plus n1 is equal to n1 plus m1. And in this case, again, to kind of shortcut it here a little bit, because the process is the same, there is m1 plus n1, which I could rewrite here. n1 plus m1 will be the exact same thing, but the order of these will be flipped. So it'll be n11 plus m11, etc. But then these entries in the matrix are real numbers, which means m11 plus n11 is the same as n11 plus m11, which means the two matrices are equal and is commutative. Next, u plus v plus w equals u plus v plus w, associativity. So pick a third one, mn, I'll go with O1, which will be defined exactly like the other ones. The problem with proving these things, especially with big matrices, they take a lot of room. Now I need to show that m1 plus n1 plus O1 is equal to m1 plus n1 plus O1. And again, this one I'm not going to write out because it gets cumbersome, but we understand what we'll do. Here, I'll add these two matrices first, which just to write the first entry would be n11 plus O11. Then I would add m1, which would make it m11 plus n11 plus O11, etc. for my entire matrix. Over here, I would add these first, so I would get m11 plus n11, etc. plus O1. But then this would then become m11 plus n11 plus O11, etc. And since these entries are real numbers, those are the exact same. In this case, it's obvious they're the exact same. So again, the proof is not all that hard, verifying the axioms. It's really just cumbersome because in this case, you have to keep writing out the matrices and then adding them using our definitions. But all we're doing is applying the definition. Matrix addition, get this. Matrix addition, get this. Matrix addition, and yes, they end up being the same. Let's see. V has a 0 vector such that for every v in u, u plus 0 equals u. In this case, clearly my 0 vector, I shouldn't have used O because now I'll do 0, but we'll say my 0 vector, that's the vector that's all zeros. So we're good so far. And clearly, again, you could check this. If I just call this, that's O1, I'll call this 0, and it's a 0 vector, but again, the vectors in my set here are matrices, so that does not mean this is a vector. It's just because it's a vector space, we call them vectors. I'll just do this notation to distinguish it from that. But I could just do m1 plus 0, and clearly if I did that, I would get m1 back. So that's clearly the 0 vector. Okay, let's see. For every u in v, there is a vector in v denoted by negative u, such that u plus negative u equals 0. Well, sure, and here it's obvious. Say if this is m1, I can clearly use the vector negative m11, negative m16, negative m41, negative m46. And if I combine this and this, I'll end up getting the 0 vector, which means I'll have an inverse. And again, the idea is this matrix has an inverse because each of the components of the matrix are real numbers, and real numbers have inverses. So I can always find the inverse of this here. Next up, CU is in V. Well, let's see. If I have this, if I do CM1, that will just be CM11, CM16, CM41, CM46. Those are all still just real numbers, which means this is still a 4 by 6 matrix, which means it's still contained in M46, which means we have closure under multiplication. CU plus V is equal to CU plus CV, but clearly here these I'm going to shortcut. If I did C M1 plus N1, just write out the sum like before, distribute the C in, that will be the same as CM1 plus CN1, where I multiply first and then combine. Again, I'm not writing these out formally because it's really straightforward, and it's just really big and messy because of the size of the matrices. Okay, C plus DU equals CU plus DU. So C plus DM1 equals CM1 plus DM1. Again, straightforward. Multiply the scalar in, you'll get C plus D M11, C plus D M16. Here, you'll get the exact same thing because you get CM11, DM11, then you'll combine them and get C plus DM11. So it's all straightforward and direct. And then CDM1 equals, so where in your book's notation, CDM1. That it doesn't matter when I multiply, but same practice. Ultimately, when I multiply here, or if I multiply the D and then the C, I'll end up getting CD M11, CD M16 on both sides, and they'll be equal. And again, I do stress, this video is going to be long enough. It's already over 12 minutes, and we're still on the first problem. So I don't want to spend another 20 minutes writing all this out. You have to formally write it out to check these things, like I did with the first few. It's just that the writing out formally is straightforward and simple, so I'm not bothering to do it here. And then lastly, you have a scalar identity. One, say M1 is equal to M1. But sure, in this case, I would actually point out here, when we think identity and we're talking about matrices, the assumption is that we are talking about the identity matrix, which only works for square matrices, which these aren't. But that is not the identity we need here. Here we need a scalar identity, which means we need the number 1 times u to equal u. And in this case, I certainly have that. If I do the scalar 1 times m1, all I'll do is distribute that in, which will give me m1 again. So just make sure we understand what we're doing. I would also point out, we got closure under addition and multiplication, which our shortcut said should give me a vector space. So these are kind of all a given, but much like other things we've done, again, recognize sometimes you'll have to prove the vector space by going through each of the 10 axioms and showing them. Other times you can shortcut it and use that approach that we did. Okay, so apparently 4 by 6 matrices form a vector space. I just erased the page number, but whatever. Next up, the set of all third-degree polynomials. We actually did this or a form of it in one of the videos, but again, if I want to show closure first, I have to show it's closed under addition. But if we think about it, pick a third-degree polynomial. So we will say P1 is equal to x cubed plus x squared plus x plus 1. Now pick another third degree polynomial. X squared plus x plus 1 minus x cubed. Those are both third degree polynomials, which means they're in that set. Now, what is p sub 1 plus p sub 2? Combined component-wise, x squared plus x squared is 2x squared. X plus x is 2x. 1 plus 1 is 2. X cubed minus x cubed is 0, and I get this. But that's not a third degree polynomial, it's a second degree polynomial. Which means if I call this the set S, this is not an S. Which means I took two elements of the set, and I got an element not in the set. So the first axiom fails. The set of all third degree polynomials is not a vector space. If we recall, and again, then you would just stop right there because you have a counterexample. When we define these, we said the set of all third degree or less polynomials. That's bad grammar, but for the way I wrote it before. Because then, when this happens, and I reduce my degree, I'm okay. So third degree or less would be fine. The only thing that would cause a problem then is if you somehow increased your degree. But whether you're adding two polynomials together or multiplying by a scalar, you never increase the degree. So that would be a vector space. If you just have a quality, you don't have a vector space. So, next. The set of all fifth degree polynomials, the exact same, so we'll do this one. Just because it looks random and weird. Number 21. The set of all xy such that number 21. X is greater than or equal to 0. And y is an element of R. Does that form a vector space? Maybe get an idea geometrically of what we're talking about. They're xy points, so they're in R2. X has to be greater than or equal to 0, so I'm over here. Y is a real number, so it can be positive or negative. So I'm essentially talking about the right half plane right here. Does that form a vector space? Well, we could run through the axioms. If I start with the first one, now, because I kind of know the ending here, we're going to shortcut this. Closure under addition. Let x sub 1, y sub 1 be one element. X sub 2, y sub 2 be another element. Then I have to add them. X sub 1, y sub 1 plus x sub 2, y sub 2 is equal to x sub 1 plus x sub 2, y sub 1 plus y sub 2. X sub 1 and x sub 2, since they're in the set, are both greater than or equal to 0, which means their sum is greater than or equal to 0, so we're good. All the y's are real numbers. If I add two real numbers, I still get a real number. So that's definitely in my set. That's closure under addition. We could check the other things, associativity, distribution, but again, much like with the matrix, these are points, vectors, whatever, but all of those will hold too, because we'll do it component-wise, just like in the matrix, and so everything will work out. So now jump to the scalar multiplication, closure. So let's see, C x1, y1. That's equal to cx1, cx2, cy1. Yeah, that's how I labeled that point. And now the question is that in my set? The problem here is C is a real number. So suppose that C is equal to -1. Then this is the point -x1, -y1. y1 is still a real number. Positive or negative doesn't matter. But x1 was positive, greater than or equal to 0. If I multiply it by a negative, this thing is now less than or equal to 0, which means it's not in my set. So this doesn't work. And it's not a vector space. If we recall somewhat, I drew these in 2 dimensions. If we tried to draw this in 3 dimensions, let's see, and now those of you who've had me in other classes know I'm not the most visual of people, but if this is x, this is y, and this is z, y can be anything, so all along this wall is fine. X has to be positive, so I have to go over here. And I'm in the plane again. So x is positive, so I'm essentially right here. This continues over this way. And I have the half plane. But we had said when looking at 3-dimensional planes, you only get a vector space if you get an entire plane going through the origin, which we don't have here. We're restricting it, we're cutting it off. We're missing a bunch of it, which is what's causing the issue here. Okay. I'm looking at some of the other ones. They're more matrix ones, polynomial ones, or versions of this. And I'm thinking I should let you do them because I kind of went through a couple here. So I should let you work through a few on your own because there'll be a similar approach to these. But the other questions I got, they said start with questions 7 and onwards. So, describing the additive inverse. In exercises 7 through 12, describe the additive inverse of a vector in the vector space. R3. What is R3? Those are triples. 0, 0, 0. I'm already thinking of the inverse. X1, Y1, XY. Let's just go with XYZ. We're not going to do multiple versions here. That's a vector in R3. What's the additive inverse? What would I add to this to end up with that? Well, clearly I would just use 0, 0, 0, because then I would get XYZ back. So that's the additive inverse, the 0 vector. Let's see. M23 is equal to 2 rows, 3 columns. So I'll just go with M11, M21, M23, M13, and M23. What's going to be my additive identity? What would I add to this to get 0? Just the 0 matrix. Pretty straightforward and simple. P4, and just so we're clear with the Brooks notation, P subscript is the set of all polynomials of degree less than or equal to n. So, P4 is equal to the set of all polynomials of degree less than or equal to 4. So pick an arbitrary polynomial. A sub 1 x to the 4th plus a sub 2 x cubed plus a sub 3 x squared plus a sub 4 x plus a sub 5. What would I add to that to get back what I started with? 0. The actual 0 polynomial, which is a polynomial. Let's see. C, your book's notation is not complex numbers. It should be continuous functions, but I will make sure. Yep. Okay. C, Negative infinity to infinity, yep. That is, my brain wants to say complex numbers because it sees the C, but we're not doing those here. That's the set of all continuous functions defined on the real line. So pick any function you want. And again, maybe pick some random ones. E to the x, f of x equals x squared, f of x equals mx plus b. I'm not proving anything here, I'm just finding the additive inverse. So just so we're clear, those are all continuous functions on the real line. What could I add to all of those to get back what I started with? 0. That is certainly a continuous function. The horizontal line along the axis, the 0 function, the constant function. And I can add it to all of those and get back what I started with. So there's my additive identity. Okay. And now it just occurs to me, the additive identities were 1 through 6. These are inverses. But for inverses, we already kind of did that. I did all the identities. To find the inverses, for any polynomial p of x, the inverse would be minus p of x. For any continuous function f of x, the inverse would be negative f of x. Again, you get to be general here because you have, say, so many functions, so many polynomials to deal with. So you can be as general as possible. Here's an arbitrary polynomial. Its inverse is the negative of that, which would then distribute the negative in, which when you combined it would cancel out, and you would end up getting the identity that we just found. For the matrices, we already did these. The inverse would just be all negatives. In R3, if you picked an arbitrary element of R3, again, x, y, z, what would the inverse be? Negative x, negative y, negative z. So they're actually pretty straightforward here. And now you have both the identities and the inverses. If there are any other questions on how to determine if something is a vector space, or more examples you'd like me to go through, feel free to let me know and I'll do more. Again, I do stress, much like other things we've done, sometimes you will be told, show this is a vector space using all 10 axioms in the definition, and you'll have to run through all of them step by step, algebraically, to show you have a vector space. Other times, once we kind of know how they work, then we'll pretty much go with just show closure under addition and scalar multiplication and you'll be good to go. Just make sure you read things carefully so you know which one it is you actually have to work with.